Welcome to our tech debt presentation on characterizing technical debt and antipatterns in AI-based systems, a systematic mapping study. This is a joint work between Justus Wagner from the University of Stuttgart and Roberto Verdecchia and myself, Ilias Georgopoulos, from the Free University of Amsterdam. Machine learning and more broadly AI-based systems are currently used to drive key business processes. These are also nowadays becoming very large and complex software systems. As you can see in the figure, they are typically comprised of several components, of which the ML code, so the actual algorithmic part, is just a small part. So AI and ML systems need to be built and maintained nowadays in a cost-effective and manageable way. And we need to better understand these decisions that may expedite the process of designing and developing such systems in the short term, but may be negative in the long term and may affect their design and development by making it more costly or impossible. In short, we need to understand and manage their technical debt. Looking at the understanding part, we try to find a comprehensive overview of technical debt in AI systems, thinking about questions such as how do traditional types of debt, such as code debt or architectural debt, manifest in AI-based systems, whether there are any new AI-specific types of technical debt in such systems, or whether there are any antipatterns that we can associate to this technical debt types. However, we could not find a comprehensive overview of technical debt in AI, and hence we decided to perform a systematic mapping study to provide such an overview and characterize technical debt in AI systems. Our study focused in three research questions. First, what are the characteristics of technical debt in AI-based systems? Second, which antipatterns have been reported for AI-based systems? And third, which solutions have been reported to address technical debt and antipatterns in AI-based systems? The design of our study is a very standard one. We started with performing an automated search on Google Scholar, looking for papers with titles that contained the word technical debt and antipatterns and also machine learning and artificial intelligence and related synonyms. We found 90 papers. We performed our inclusion and exclusion criteria, out of which we selected 5 papers. Then we performed 4 iterations of both forward and backward snowballing, leading to a final set of 21 papers, which were our primary studies. Then we performed data extraction and data synthesis, where we also did open Excel coding, and we wrote the report. Now I will hand over to Roberto, who will talk about the results of our study.
Thank you, Ilias, and hello to everyone. I'm going to briefly guide you through our findings on how technical debt is characterized in AI-based systems. And we structure our findings around 2 taxonomies of technical debt types, namely the one presented by Lee and others and the one presented by Rios and others. First of all, we have a look at the established technical debt types. So the technical debt types which do not showcase differences in AI-based systems if compared to non-AI-based systems. And here we see the most recurrent technical debt type is people debt, followed by documentation debt and requirements debt. Interestingly, architectural debt, test debt, and versioning debt do not appear at all in their established form in our findings. Where our results start to get interesting is when we have a look at the variation of technical debt types in AI-based systems. And here we see that the picture completely changes. The most recurrent variation of technical debt type is infrastructure debt, which now regards the implementation and operation of AI pipelines, which can be extremely cumbersome if multiple AI pipelines occur in an AI-based system. This debt type also regards the suboptimal allocation of AI resources and weak AI model monitoring capabilities. The second most recurrent variation is architectural debt, which actually exclusively showcases variations, reflecting the deep entanglement that architectural components in AI-based systems have with the underlying data sets which are used. The third most recurrent type is code debt, which reflects the experimental nature of AI-based systems and can lead to the appearance of dead experimental code paths or suboptimal refactoring of experimental models in order to make them production ready. Test debt is another category which exclusively showcases variations, and this case regards deficiencies in testing AI models and pipelines, from the naive omissions of basic sanity checks to the lack of more sophisticated tests to assess data quality and distributions. Versioning debt is another type of debt which exclusively displays variations and now regards the versioning of AI models and training or testing data. And this process in AI-based systems is often carried out suboptimally or even completely neglected. In our study, we also identified 4 new debt types, the first one of which is data debt, which regards the collection, management, and usage of data, both for training and production. This type of debt can be hard to detect and poses a risk on the long-term evolution of an AI-based system. It mostly regards data quality issues, unmanaged data dependency as anomalies, or poor data relevance. The second new type of debt is model debt, which regards suboptimal practices in the design, training, and management of AI models. This can rise to the suboptimal feature selection processes, neglected hyperparameter tuning, and poorly engineered model deployment strategies. The third new debt type is configuration debt. That while in AI-based systems configuration lines often exceed the source lines of code, configurations are not given the same level of quality control, leading to massive or complex configuration files which are poorly understood, documented, or versioned. Finally, the last new debt type we identified is ethics debt. So deficiencies around the ethical aspects of AI-based systems, such as algorithmic fairness, prediction bias, or lack of transparency and accountability. Given the deep embedment that this type of debt can have in the AI-based system, this debt type can lead to complete restructuring and retraining of AI models, or even to legal consequences. Finally, we can have a look on the quality attributes which are affected by technical debt in AI-based systems. And here we see the most recurrent quality attribute is functional suitability, in particular if we consider the subcharacteristic of functional correctness. Then of course we have maintainability, with particular emphasis on modifiability, testability, and reusability. In our study we also identified additional quality attributes which are impacted by technical debt in AI-based systems, such as, for example, observability, reproducibility, transparency, and fairness. I now leave the word to Justus, who will guide us through the rest of our findings.
Hi everyone. I will now guide you through the results of research question 2 and research question 3 and then close out with a conclusion. Let's start with antipatterns. From the 21 studies, we extracted and synthesized 72 unique antipatterns that we then classified into 6 different categories, with subcategories for the larger ones. The most prominent categories were model and data antipattern, where the majority of the antipatterns are located. We have also smaller categories, namely design and architecture, code, infrastructure, and ethics antipatterns. Let's have a look at the 3 largest categories. We identified 29 antipatterns related to deficiencies or suboptimal practices around AI models, so mostly relevant in the context of machine learning. An example of this is the antipattern direct feedback loops. Here, the predictions of an AI system are used to inform decisions that in turn may have an influence on the training data selection for that same system. So we have a harmful and potentially self-sustaining relationship that can lead to biased decisions. Another example here is training serving skew, which refers to the fact that we have a significantly reduced prediction quality in the production system in comparison to the training or development environment. Reasons for this can be different code path in production to compute features, or that the data in production, so the incoming calls to the system, are very different to the training data that has been used. The second largest category was data antipatterns, where we identified 22 unique instances. These were often related to data quality or data anomalies, for example, null or missing values or miscoded data. But antipatterns were also related to the relevance of data. So one antipattern was emphasis on available data instead of the most relevant data, or the over-curation of data. So gathering data that is so specific that it won't generalize well. A more complex antipattern in this category was unstable data dependencies. Here, our AI system uses data from external systems or components that may change over time. And if this data changes, it is unstable, this may have a significant effect on our prediction quality if it is used, for example, to compute features. With 8 identified antipatterns, design and architecture was a smaller category. However, most of these antipatterns were mentioned several times in the literature. An example here would be undeclared consumers. If the prediction output of our AI system is used by other systems or components without our knowledge, then this creates a hidden dependency. If now our output changes over time, without us knowing which other systems or components will consume it, then this can have a significant effect on these other systems. A second example would be glue code, which refers to the state where a system is composed mostly of general purpose packages that are stitched together by customly written code, for example, for loading and transforming data. On an architectural level, this can be described as pipeline jungles. And in both cases, we may have messy interconnections and dependencies that make it hard to keep an overview of the system. Lastly, I want to talk about some solutions proposed in the literature to address technical debt and antipatterns in AI-based systems. In total, we extracted 46 solutions. Some of these solutions address a certain technical debt type, like data debt, and some address a specific antipattern, like training serving skew. Then we had some solutions that were rather generic methodological proposals, like perform extensive testing. And lastly, we had a few concrete tools or frameworks, like a data quality advisor for machine learning. Some solutions were proposed frequently. For example, one solution was to explicitly manage your model configuration. This solution suggests to use the same treatment for model configurations as you would for source code, so reviews and versioning, for example. Another proposal was to use clear component and code APIs to combat glue code and pipeline jungles. If you hide your packages behind custom interfaces, then you are also robust towards swapping out general purpose packages. And lastly, one proposal was to remove unnecessary features. Features come with a cost, and if a feature does not bring much improvement for accuracy, then it is called an epsilon feature and should be removed. So to conclude, we conducted a mapping study and identified 21 publications about technical debt and antipatterns in AI-based systems. By analyzing these studies, we observed that existing types of technical debt show variations in these systems. We also identified 4 new types of technical debt. We also extracted 72 unique antipatterns and categorized them in 6 different groups. Lastly, we identified 46 solutions to address technical debt or antipatterns in AI-based systems. Our results can help industry to raise awareness for these concepts, to support communication about them, and some of the collected solutions may help to address these concepts. For academia, our research may serve as a foundation for future studies in this area. because, based on the results, we are confident that more research is needed to understand, identify, and especially address technical debt and antipatterns in these systems. Thank you for your attention.
Okay, so thanks again for the first presentation. Now it's time to move to the last paper of the day, that is entitled Characterization, Technical Debt and Antipatterns in AI-Based Systems, a systematic literature review. Here we have all the three authors in the backstage. So the presentation is pre-recorded, and then we will provide the question at the end of the presentation. Thanks.
Welcome to our tech debt presentation on characterizing technical debt and antipatterns in AI-based systems, a systematic mapping study. This is a joint work between Justus Bogner from the University of Stuttgart and Roberto Verdecchia and myself, Ilias Gerostatopoulos, from the Free University of Amsterdam. Machine learning and more broadly AI-based systems are currently used to drive key business processes. These are also nowadays becoming very large and complex software systems. As you can see in the figure, they are typically comprised of several components, of which the ML code, so the actual algorithmic part, is just a small part. So AI and ML systems need to be built and maintained nowadays in a cost-effective and manageable way. And we need to better understand these decisions that may expedite the process of designing and developing such systems in the short term, but may be negative in the long term and may affect their design and development by making it more costly or impossible. In short, we need to understand and manage their technical debt. Looking at the understanding part, we try to find a comprehensive overview of technical debt in AI systems, thinking about questions such as how do traditional types of debt, such as code debt or architectural debt, manifest in AI-based systems, whether there are any new AI-specific types of technical debt in such systems, or whether there are any antipatterns that we can associate to these technical debt types. However, we could not find a comprehensive overview of technical debt in AI, and hence we decided to perform a systematic mapping study to provide such an overview and characterize technical debt in AI systems. Our study focused in three research questions. First, what are the characteristics of technical debt in AI-based systems? Second, which antipatterns have been reported for AI-based systems? And third, which solutions have been reported to address technical debt and antipatterns in AI-based systems? The design of our study is a very standard one. We started with performing an automated search on Google Scholar, looking for papers with titles that contained the word technical debt and antipatterns and also machine learning and artificial intelligence and related synonyms. We found 90 papers. We performed our inclusion and exclusion criteria, out of which we selected 5 papers. Then we performed 4 iterations of both forward and backward snowballing, leading to a final set of 21 papers, which were our primary studies. Then we performed data extraction and data synthesis, where we also did open Excel coding, and we wrote the report. Now I will hand over to Roberto, who will talk about the results of our study.
Thank you, Ilias, and hello to everyone. I'm going to briefly guide you through our findings on how technical debt is characterized in AI-based systems. And we structure our findings around 2 taxonomies of technical debt types, namely the one presented by Lee and others and the one presented by Rios and others. First of all, we have a look at the established technical debt types. So the technical debt types which do not showcase differences in AI-based systems if compared to non-AI-based systems. And here we see the most recurrent technical debt type is people debt, followed by documentation debt and requirements debt. Interestingly, architectural debt, test debt, and versioning debt do not appear at all in their established form in our findings. Where our results start to get interesting is when we have a look at the variation of technical debt types in AI-based systems. And here we see that the picture completely changes. The most recurrent variation of technical debt type is infrastructure debt, which now regards the implementation and operation of AI pipelines, which can be extremely cumbersome if multiple AI pipelines occur in an AI-based system. This debt type also regards the suboptimal allocation of AI resources and weak AI model monitoring capabilities. The second most recurrent variation is architectural debt, which actually exclusively showcases variations, reflecting the deep entanglement that architectural components in AI-based systems have with the underlying data sets which are used. The third most recurrent type is code debt, which reflects the experimental nature of AI-based systems and can lead to the appearance of dead experimental code paths or suboptimal refactoring of experimental models in order to make them production ready. Test debt is another category which exclusively showcases variations. In this case regards deficiencies in testing AI models and pipelines, from the naive omissions of basic sanity checks to the lack of more sophisticated tests to assess data quality and distributions. Versioning debt is another type of debt which exclusively displays variations and now regards the versioning of AI models and training or testing data. And this process in AI-based systems is often carried out suboptimally or even completely neglected. In our study, we also identified 4 new debt types, the first one of which is data debt, which regards the collection, management, and usage of data, both for training and production. This type of debt can be hard to detect and poses a risk on the long-term evolution of an AI-based system. It mostly regards data quality issues, unmanaged data dependencies, anomalies, or poor data relevance. The second new type of debt is model debt, which regards suboptimal practices in the design, training, and management of AI models. This can rise to the suboptimal feature selection processes, neglected hyperparameter tuning, and poorly engineered model deployment strategies. The third new debt type is configuration debt. That while in AI-based systems configuration lines often exceed the source lines of code, configurations are not given the same level of quality control, leading to massive or complex configuration files which are poorly understood, documented, or versioned. Finally, the last new debt type we identified is ethics debt. So deficiencies around the ethical aspects of AI-based systems, such as algorithmic fairness, prediction bias, or lack of transparency and accountability. Given the deep embedment that this type of debt can have in the AI-based system, this debt type can lead to complete restructuring and retraining of AI models, or even to legal consequences. Finally, we can have a look on the quality attributes which are affected by technical debt in AI-based systems. And here we see the most recurrent quality attribute is functional suitability, in particular if we consider the subcharacteristic of functional correctness. Then of course we have maintainability, with particular emphasis on modifiability, testability, and reusability. In our study we also identified additional quality attributes which are impacted by technical debt in AI-based systems, such as, for example, observability, reproducibility, transparency, and fairness. I now leave the word to Justus, who will guide us through the rest of our findings.
Hi everyone. I will now guide you through the results of research question 2 and research question 3 and then close out with a conclusion. Let's start with antipatterns. From the 21 studies, we extracted and synthesized 72 unique antipatterns that we then classified into 6 different categories, with subcategories for the larger ones. The most prominent categories were model and data antipattern, where the majority of the antipatterns are located. We have also smaller categories, namely design and architecture, code, infrastructure, and ethics antipatterns. Let's have a look at the 3 largest categories. We identified 29 antipatterns related to deficiencies or suboptimal practices around AI models, so mostly relevant in the context of machine learning. An example of this is the antipattern direct feedback loops. Here, the predictions of an AI system are used to inform decisions that in turn may have an influence on the training data selection for that same system. So we have a harmful and potentially self-sustaining relationship that can lead to biased decisions. Another example here is training serving skew, which refers to the fact that we have a significantly reduced prediction quality in the production system in comparison to the training or development environment. Reasons for this can be different code path in production to compute features, or that the data in production, so the incoming calls to the system, are very different to the training data that has been used. The second largest category was data antipatterns, where we identified 22 unique instances. These were often related to data quality or data anomalies, for example, null or missing values or miscoded data. But antipatterns were also related to the relevance of data. So one antipattern was emphasis on available data instead of the most relevant data, or the over-curation of data. So gathering data that is so specific that it won't generalize well. A more complex antipattern in this category was unstable data dependencies. Here, our AI system uses data from external systems or components that may change over time. And if this data changes, it is unstable, this may have a significant effect on our prediction quality if it is used, for example, to compute features. With 8 identified antipatterns, design and architecture was a smaller category. However, most of these antipatterns were mentioned several times in the literature. An example here would be undeclared consumers. If the prediction output of our AI system is used by other systems or components without our knowledge, then this creates a hidden dependency. If now our output changes over time, without us knowing which other systems or components will consume it, then this can have a significant effect on these other systems. A second example would be glue code, which refers to the state where a system is composed mostly of general purpose packages that are stitched together by customly written code, for example, for loading and transforming data. On an architectural level, this can be described as pipeline jungles. And in both cases, we may have messy interconnections and dependencies that make it hard to keep an overview of the system. Lastly, I want to talk about some solutions proposed in the literature to address technical debt and antipatterns in AI-based systems. In total, we extracted 46 solutions. Some of these solutions address a certain technical debt type, like data debt, and some address a specific antipattern, like training serving skew. Then we had some solutions that were rather generic methodological proposals, like perform extensive testing. And lastly, we had a few concrete tools or frameworks, like a data quality advisor for machine learning. Some solutions were proposed frequently. For example, one solution was to explicitly manage your model configuration. This solution suggests to use the same treatment for model configurations as you would for source code, so reviews and versioning, for example. Another proposal was to use clear component and code APIs to combat glue code and pipeline jungles. If you hide your packages behind custom interfaces, then you are also robust towards swapping out general purpose packages. And lastly, one proposal was to remove unnecessary features. Features come with a cost, and if a feature does not bring much improvement for accuracy, then it is called an epsilon feature and should be removed. So to conclude, we conducted a mapping study and identified 21 publications about technical debt and anti-patterns in AI-based systems. By analyzing these studies, we observed that existing types of technical debt show variations in these systems. We also identified 4 new types of technical debt. We also extracted 72 unique anti-patterns and categorized them in 6 different groups. Lastly, we identified 46 solutions to address technical debt or anti-patterns in AI-based systems. Our results can help industry to raise awareness for these concepts, to support communication about them, and some of the collected solutions may help to address these concepts. For academia, our research may serve as a foundation for future studies in this area, because, based on the results, we are confident that more research is needed to understand, identify, and especially address technical debt and anti-patterns in these systems. Thank you for your attention.
My pronunciation ist nicht schlecht.
Ah, sehr gut.
Ja, sehr gut.
Oh
Ich
my
spreche
gosh.
ein bisschen.
Ah, siehst du? Ich
Ja.
wusste es.
Okay, guys, I can understand some things, but
We go live. Okay. So thank you very much for your presentation. Now we have on the stage all the 3 authors of this paper. So we have one question from the audience, from Alexander. Alexander say very interesting findings, and I also agree with the sentence of Alexander with his feeling. But the question is, could you provide some example of infrastructure debt in AI-based system? Alexander is wondering whether these actually refer to performances, scalability, cost issues, experience when running software.
I can take this one. Thank you for your question, really interesting. It also relates to performance, scalability, and cost. So what we found is one instance of infrastructure debt is when you have various AI pipelines, which then creates an overall complex infrastructure to manage. Or another instance is the suboptimal allocation of resources for training testing, which leads to performance issues, both in terms of efficacy and effectiveness, let's say. And then we also saw another instance of infrastructure debt is weak AI monitoring and debugging capabilities, which then reflect in infrastructure.
Yes, there are other. Okay, Justus,
maybe
if you want to add some insight.
Yeah, I can add something. In AI-based systems, we also have the case that the distinction between the infrastructure and the architecture of the system is not that clear in all cases, because the data pipelines, so the infrastructure that feeds the system continuously with new data, is such an important part of the system that you could also argue that it actually becomes part of the architecture of the system. So it's not such a clear distinction. It's very, very interwoven and messy in some places.
Okay, so thank you very much. We have 1 minute left, so I have to do the wrap up. Of course, again, there is the joint discussion room from your paper. I would like to thank all the presenters of all the 2 sessions, the keynote. That was really, really amazing insight topics. And we will see tomorrow for unfortunately the last day of Tech Debt, and with other papers, with other keynote, with the lightning talk, and with much more inside. So from our side, from the organizational committee, thank you very much to be also there in the second day. And if you have other further questions for Roberto, Justus, and Ilas, you can start to formulate also in the chat, and then move on to the discussion room. Thank you very much. So we can directly move to the